Okay. Yes, as you may have guessed from the title of my presentation, today I will not be focusing about Wolf-Rayet stars specifically, but I will be talking about generally astrophysical scenarios where the radiation or the light can dominate the structure and dynamics of such an astrophysical scenarios. And as a very cartoonish example, here I'm showing the light as a light bulb, which is in case of stellar atmospheres, pushing against the gravitational field of the star and driving the stellar outflows. So in general, the radiation field or radiation can be important on many different scales in vast majority of astrophysical scenarios. For instance, starting from the solar sun, radiation can dominate the internal energy or energy exchange. On the larger scale of hot massive stars, radiation dominates not only the energy budget of the stellar outflows, but also the momentum budgets. It can influence the disks around stars by ablating and evacuating disks. And on even larger scales of disks around supermassive black holes, such as in ectogalactic nuclei, it can have feedback on super Eddington accretion. And even on larger scale, on the universe scale, it can generally influence the formation of very massive, first very massive stars. But today's talk will be mostly focused around the winds of hot massive stars. Now, to study such an astrophysical environments, there are two approaches that one can take: as a retrieval or getting the information that we need or we are after, such as luminosity, mass of the stars, by direct imaging or by from the spectrum coming from the stars. Or another approach is to have initially assumed input parameters and then do the forward modeling by assuming some kind of input physics. And as you may have guessed from this red box, today I will be focusing on the later type, where I will try to build the presentation towards showing you the nice simulation, example of which I'm showing you here at the bottom. But before we move to that, let's have a look at some of the other very nice numerical results connected to this topic. The first example that I want to show you is wind outflows from hot massive stars. In this case, you will see the simulation where the star is located at the bottom of the slide. Then along the vertical line, we have the radius, and on the panels, you will see the time variation of density and radial velocity. So as you can see from this very nice simulation done by my fellow PhD student, Florian Grissen, you will see that very dynamical, clumpy, supersonic outflows are formed. Now to move to other nice applications or numerical results, we can also simulate disks around, in this case, BE stars, whereas an irradiation coming from the disk will influence the outer layers of the disk, ablating it. And what you will see here will be the projection or cut through the disk, and you will see a variation of the density inside the disk. As you can see, the radiation from the star causes outer layers of the disk to turn into a wind and slowly evacuates the wind away from the star. Now, other interesting similar disks, but on the more larger scales, are the disks, accretion disks around the supermassive black holes, now represented with this pink line and supermassive, not pink, but blue line, but supermassive black hole with this black dots. In the case of such an accretion disks, then the radiation coming from disk itself can drive the wind outflows away from the surface of such a disk. So the question is why we might be interested in such scenarios. Why are we investigating all of those different cases? Well, the answer for the winds is simple. The wind outflows influence evolution of the stars, as well as can determine or influence the creation of black remnants after their death, such as in black holes. In case of these stars, evacuation of the disk by the radiation can explain why or rarity of the OE stars, for instance. And in case of active galactic nuclei, such as wind outflows along with jets can feedback not only the star formation rates, but also quench the growth of such a host supermassive black holes. Now, if you are intrigued by those simulations and you want to do them yourselves, the recipe how to do such a simulations will be to take your favorite hydrodynamics code and then in your hydrodynamics code account for radiation. And this radiation will be what I will focus today throughout my talk, how to account for the radiation in such a hydrodynamic codes or scenarios. And today's talk will be split into two parts, where first I will talk about radiation hydrodynamics, introduce how the radiation force is computed, and try to build up towards generalized formalism, which we are trying to develop here. And then I will show you some of our very first results using our generalized formalism. A bit about radiation hydrodynamics. Generally, what is hydrodynamics is a description of how fluids or gases change throughout the time. And for hydrodynamics, we use conservation equations, where on the left-hand side, you will have variation of quantity, and on the right-hand side, you will have sources and things that cause this quantity to vary. In hydrodynamics, we are interested in three equations mostly, which are mass conservation, momentum, and energy conservation. And as you can see, the radiation force comes as a momentum source in equation of in momentum conservation, as well as plays a role in equation of energy conservation through providing the mechanical energy, but heat as well as internal or heat energy. But today I will mostly focus on radiation force as a source of momentum. Then question is, what is a radiation force? Well, generally, radiation force will be force that gases or liquids will experience due to interaction with radiation. If we want to quantify this radiation force, we need to know what is the interaction, how does radiation and gas interact, which is described by the coupling between radiation and gas through opacity, as is K kappa here. We need to know intensity or radiation itself, and then we can integrate over the full frequency domain for a given direction and solid angle. But interesting question then is, what is coupling between radiation and the gas? The coupling can take many different forms and shapes, and understanding and quantifying this coupling between radiation and gas is one of the key questions in describing the radiation force. And today, I will focus on two mechanisms how radiation can be coupled to gas. First, I will discuss a simple case of radiation scattering on electrons, and then I will discuss a bit more complicated case where radiation will interact with electrons that are in a bound state of atoms. So first, let's have a look at the scattering on free electrons. What this picture, or what I'm trying to tell you with this picture, is that in such a scenario, incoming radiation represented by this green photon will interact with a free electron, scatter it away, providing some momentum, and it will then be deflected to some direction. If we are dealing with such a scattering events, then opacity or the coupling can simply be described using so-called Thomson opacity. As you can see, it will in this case be constant. And then if we are interested in stellar atmospheres, and we only consider spherically symmetric cases with the radial variation, then the radiation force can be simply given as this opacity times the radiation flux. We can, for such a cases, we can also introduce so-called Eddington ratio, which is ratio between radiation force and the gravity. And since radiation flux and gravity both vary as 1/r², such an Eddington ratio for electron scattering in this case will only depend then on luminosity and mass ratio of the star. If we now quickly estimate what this Eddington ratio for a sun will be, you will immediately be convinced that it's very small, it's 10 to minus 5. That's why, for instance, for sun, radiation does not provide much of a momentum. However, since for massive stars, luminosity can quickly increase with increase of mass, we can find scenarios for massive stars where such an electron scattering already provides quite a large momentum, and this Eddington ratio can be in the range of 0.1 to 0.5, which is quite a large number, meaning that in case of 0.5, the radiation force is half of the gravity, only for electron scatterings already. Now, if we move to second case, which I will be discussing, which is interaction of radiation with electrons inside the atoms. The simplest case that we can set up is a case where we have two levels represented here by this Rothian diagram, where radiation can excite electron from one energy level to another, or radiation can be released, photon can be released when electron is de-excited from one higher level to lower level. So if we are considering such a cases, to build some intuition, it's useful to draw a parallel of such a quantum process with a simple weakly damped driven harmonic oscillator. From our knowledge of classical mechanics, we know that such an oscillating resonating systems can be described, or amplitude of such a system can be described with Lorentzian. And in this case, the Lorentzian will describe also the probability of photons interacting with such a system, which is now given as a cross-section. And as you can see, this cross-section will depend then on the frequency of incoming photon, as well as the resonance frequency or characteristic frequency of such a transition. Then the total interaction probability will be described by this so-called classical cross-section. For such a resonant systems, we can also estimate how important this process can be by quantifying so-called resonance quality, which in this case will be dependent on the ratio between this classical cross-section or total interaction probability and the interaction probability of photon interacting with free electrons described by this Thomson cross-section. And if we then estimate this resonance quality for such a line as Lyman alpha, we can see that it is very, very large number, meaning that there is lots of potential in such a processes. However, the cross-section is not what we need to compute the radiation force. It is actually the opacity that we need. But it is quite simple to relate the cross-section with opacity by means of number density of species in interest and total mass density. In case of Lyman alpha, this number density will represent the number density of ground state of hydrogen. And it is also quite useful and insightful to estimate the relative strength of such a process relative to the Thomson opacity or Thomson scattering. And as you can see, such a relative strength will depend on, first of all, on our resonance quality, on the ratio between number densities of species in interest and electron number density, as well as oscillator strength, which will be the quantum mechanical correction to our classical picture of harmonic oscillator. then the radiation force can be simply computed from the radiation force of electron scattering and these strengths of such a processes. If we then estimate this little q parameter or relative strength, again for Leuven alpha, assuming that most of hydrogen is ionized, we can see that this relative strength can be very large, on the order of thousands. However, we also need to keep in mind that in order to compute the radiation force itself, we also need to know what is the flux at resonance wavelength or resonance frequency. Since this is the resonant process and only the flux at the given frequency of resonance can excite such a process. However, as you can see on this plot here, where on the x-axis I plot 1 over nu or lambda, and on the y-axis I show this normalized flux. As temperature changes, the location where the flux maximum occurs will be shifted. And if then you compare the location of flux maximum to the location where, for instance, our Leuven alpha is, you can see that in case of cooler temperatures, this basically gives no flux, therefore there will be very little radiation force. However, if flux maximum is well aligned with line center or resonant frequency, then this such a process can give extremely large radiation force. Note, however, that I put an indicator thin, meaning that now I consider line to be optically thin. Later in my talk, I will relax this assumption as well. Now, if I show you such a Protean diagram again, but not a doodle, but an actual Protean diagram for one of the ions, you will see that there are many, many levels and even more transitions between levels, many more lines. And if we now have a look at the table for which I took from radiative transfer code phosphine database, where I just show how many lines are available for different species, you can see that such a database can account for millions of lines, in this case, more than 4 million of lines. And the question arises, how do we account for all of these millions of lines in our codes? Well, the first and simplest approach will be to assume that our medium is static and that we are in a local thermodynamic equilibrium. And then we can compute an average, in this case, Rosland mean average opacity as a function of different temperatures and densities. Such tabulations of Rosland mean opacities normally come in a shape of opal tables, for instance. And on this plot here, where x-axis will be the logarithm of temperature and y-axis is the logarithm of density, I show example of one of such tabulations from opal. And what I show in color is relative radiation force relative to the electron, radiation force from electron scattering. And as you can see, as a function of temperature and density, such tabulated values of Rosland mean opacity can vary by a lot. And even in the regions like indicated here, where more and more lines come available through as iron recombines, such a force can have a significant contribution. However, if we now have a look at the typical densities and temperatures characteristic for the stellar outflows, we will see that this type of opacity does not provide much of a force. In any case, such tabulations are very useful and have extremely wide range of applications, such as in stellar structure and evolution computations. But keep in mind that the main assumption here was that we are in a static, we are describing static medium, meaning that we are neglecting dynamical effects. If we do not neglect dynamical effects, what will happen as their velocity changes, now represented by this blue line, velocity increasing as a radius, the lines, now here in this black doodles, can be Doppler shifted away from their rest frequency or rest wavelengths, allowing them to absorb more flux than they would have if they were stationary. In such a case, as you can see on this diagram here, where I show the radiation force from one of our dynamical simulations as a function of velocity, there might be drastic increase of radiation force, especially as compared to such a Rosland mean opacity, where I plot the Rosland mean opacity as a red line at the bottom, and such a Doppler shift enhanced opacities as a blue line here. Unfortunately, to account for those effects generally in our simulations is extremely hard challenge, and it can only be done by a handful of codes such as a fast-wind, power, or CMFGen, where they can account for millions of lines, but in 1D steady-state scenarios. Otherwise, for most of other applications, such effects are either approximated or completely neglected. And what I will try to build in the following parts of the presentation is a general formalism which is versatile and simple enough to account for all of those processes in our numerical simulations. And then I will show how we implement that and use it inside the Radiation-Hydrodynamics code MPI AMR. So toward building the generalized formalism, our approach will be to account for many different lines, to include the Doppler enhancement, and to also account for the optical depth of each contributing lines. Then, using so-called Sobolev approximation, which allows us to describe the variation of intensity as a local function of relevant parameters such as the strength of each line. We can, using Sobolev assumption, we can describe the variation of intensity as just exponential decay, whereas then this optical depth of the line will be function of strength of the line as well as this little t parameter, which will be the effective strength of the line if it had electron scattering opacity. Note here that this little t parameter is independent of line properties and depends only on hydrodynamical variables that will come important later in the slides. So in such a case, we can then generalize our expression for a single thin line to a sum over all contributing lines, whereas then each different line will be assigned different I index, and we sum over all those contributing lines. The term in the red square here then will account for optical depth of each of those lines. Note, however, is that in order to compute the line strength, as shown, as you could see previously, we also need to know the number density of species in interest. And to this end, we are using the LTE assumption, which allows us to use Saha and Boltzmann relations in order to compute the number densities. Now, if we take combination of temperature and density and compute this radiation force as a function of this little t parameter, we can arrive to this plot here, where I show how radiation force on the y-axis changes as a function of this effective optical depth for a given combination of temperature and density. To compute this radiation force, I have used a line database coming from the fast winds. Here, we will distinguish two two important parts of the diagram, optically thick and optically thin regions. As you can see, optically thick region follows so-called power law, which means that the radiation force will be expressed as a sum power, as a T to the sum power. However, as we move towards the optically thin region, instead of radiation force increasing to very large values, it quickly saturates to a single radiation force that we can get in optically thin regime. To describe such a well, we can compute such a radiation force for many different temperatures and densities. However, it is useful rather than quantifying the radiation force as a function of T to get some understanding of how line distribution behaves as well. So the idea is that instead of taking the taking the sum over all lines, we want to describe a statistical distribution of lines, which in this case, we use this distribution introduced by Galea in '95, follows the exponentially truncated power law. Then if we take the integral over such a distribution, we can arrive to the radiation force expression, which will then depend on three parameters: Q bar, Q naught, and alpha. As you can see from the plot here, which is the same plot as before, the Q bar then will describe the maximum force that is available in optically thin regime. The Q naught will describe the transition between optically thin to optically thick regimes, while alpha describes the power law index in optically thick region. This exercise can be repeated for combinations of many different temperatures and densities. And for those temperatures and densities, we can find how Q bars, Q naughts, and alphas change, giving us such a variation maps of those parameters as a functions of density and temperature, which will then allow us to compute radiation force where we're interested or where we are interested. Since this is also a tabulated value, we can compare these tabulated values to other tabulations, such as opal tabulations of Rosland-Mean opacities. But keep in mind that unlike the Rosland-Mean opacities, such a tabulations allow us to compute radiation force accounting now for dynamic effects as well, which means that it has much wider range of applicability, which can vary from winds across the stellar winds, disk winds, or disk ablation, and many other interesting cases. Now, moving back to how we implement or how we use it, generally, what we have from radiation codes, as given by this example plot here, is example plot of one of our wind simulations is variation of density and temperature as a function of radius, as a function of coordinates. So we will have densities and temperatures for each numerical cell. Then using combination for each numerical cell, we can find corresponding parameters in the table, which will give us the radiation force for that particular numerical cell. Then we can iterate to update our simulations throughout the time, accounting self-consistently for radiation force. So this brought me to the second part of my presentation. In the first part, I tried to show you the generalized frameworks that we use, but now I will try to show you some of our first results. So let's first start with this artist impression of Hertzsprung-Russell diagram, where you can see stars arranged by their effective temperatures and luminosities. The first interesting candidates, which we applied our method to, are O stars. And the massive stars, O stars have stellar outflows, and the mass loss rate or determination of exact mass loss rates is important to understand their evolution. Thus, they serve as a perfect candidates. And what I will show you in simulations that will follow is a simulation for O star with parameters like zeta puppies, where we'll see as a function of time how velocity and radiation force will relax. We will also see how mass loss rate will relax to its self-consistent value. So as you can see from this simulation, the relaxation was quite fast, and it relaxed to its steady-state solution with a mass loss rate that is quite in line with what is expected for such a star. However, I will also emphasize that the velocities that we get in such a simulation are slightly on the lower side. Now, what we can do is also to compute such a mass loss rates and velocities for a grid of O stars. And for this, we use the grid of O stars initially used by Björklund et al. To compute their mass loss recipes using full NLT radiative transfer code FastWind. As you can see on these plots, where luminosity is on the x-axis and the mass loss rate is on the y-axis, the mass loss that Björklund et al. Compute from their full NLT simulations are given in the red line, and the mass loss rates that we get from our hydrodynamic simulations are given in a blue dots. And as you can see, there is quite a they are quite in line. There is quite a remarkable agreement between those two. And both agree and both of mass loss rates are lower than typically used mass loss rates in stellar evolution coming from Inc et al. Now, what is important to point out here is that there is large difference between methods or how those mass loss rates are computed, and the most difference is in the computational time scales. If you compare the time that one FastWind model will take to compute the steady state structure with self-consistent mass loss rate, it will be on the order of days, whereas our hydrodynamic simulation takes time on the order of minutes, up to 10 minutes, which is extremely large increase in computation or decrease in computational times, meaning that we can afford more computations in a given time. Plus, this is numerical hydro model, which means that our models are time dependent, accounting for time dependent variations. And it is also easily scalable for multi-dimensions, meaning that we can scale our computations from 1D to 3D. Now, I have pointed out that as we both predict, the mass loss rates are lower than generally used in stellar structure and evolution study. And then the question is, what influence does it have on, for instance, stellar evolution? What I show here is the variation of effective temperature and luminosity of the stars across the Hertzsprung-Russell diagram, again, where temperature is y-axis and luminosity is other way, temperature is x-axis and luminosity is y-axis. And I compare two evolutionary tracks of a star which had standardly used mass loss rates versus the stars that was computed using these reduced mass loss rates. As you can already see from this plot, there is vast difference in their evolution pathway. Also, with our reduced masses, what you can see is that we have trouble forming so-called classical Wolf-Rayet stars, which are end stages of such a massive star evolution, located in the very left corner of such a diagram with reduced mass loss rates. Also, if mass loss rate is reduced, it means that less mass is lost throughout the evolution of such star, which can also mean that we can produce higher mass black holes. But however, mass loss rates on the main sequence is not unique mass loss mechanism. Stars can lose their mass in different different evolutionary stages as well, such as in luminous blue variables or yellow supergiant stages, meaning that this scenario will, or this evolutionary track will be modified if we include the mass flow traits on these stages as well. Another way how we may again form Wolf-Rayet stars is through binary interactions, since we know that quite a significant number of observed Wolf-Rayet stars come in binary. So this brings me to the topic of Wolf-Rayet stars. Now, Wolf-Rayet stars, on our Hertzsprung-Russell diagram will be located somewhere here. As I mentioned, they are end evolutionary stages of massive star evolutions, and since they are thought to be progenitors of exotic objects such as black holes, it's quite interesting to study those objects. Now, if we build on our previous work, what I will show you here is a simulation of such a Wolf-Rayet outflow, where I show the variation of densities throughout the time in such an outflow. As you can see, throughout the time, quite a dynamical, clumpy atmosphere is formed, or outflow is formed with quite a high mass loss rate, and as a matter of fact, with a low clumping factors. Now, as a future applications, this method can be applied to wider range of to study stars across the Hertzsprung-Russell diagram. This method is quite well suited also to study rapidly rotating stars, where normally for these stars, a mass loss rate is assumed from standard recipes. However, in our case, we can compute it self-consistently. And this method can be also applied to such as disk winds or disk ablation simulations, giving all self-consistent simulations for those different scenarios. So to give a bit of summary, I hope that today I convinced you that radiation force or radiation generally is quite important in astrophysical environments. I tried to give you an overview of our method, how we can account for radiation force coming from millions of lines in our numerical simulations. And I also gave you a bit of overview on one of our very, very recent results. As well as I tried to convince you that such a method has quite a wide range of applicability. As a conclusions, I want to emphasize that our recent results agree that mass loss agree with Bjorklund et al. Prediction that mass loss rates on the for the O stars is less than generally assumed ones. I also demonstrated you that Wolf-Rayet winds can be very dynamic and maybe inherently multidimensional systems. And to give you a bit of future work, we are planning to increase our line database, as well as try to move towards a generalized non-LTE description. Thank you.
Thank you very much, Luka. So if there are any questions, please mention this in the chat. I will call out your name. There seems to be, yes, Dominic, please.
Hi, Luka, thanks for that.
Hello.
Can you comment on the divergence of the Bjorklund et al. Prescription? And so you had red and blue lines in one of the slides. I forgot the number.
Yeah,
sure.
So you mean
the low luminosity end? Yeah. Do we understand why these are becoming divergent?
We have guesses that this might be caused due to so-called source function dips, but this is just initial speculations. We still have to analyze those results. As I said, they are extremely large. However, I think this should be related to the difference between methods and descriptions, not.
Okay, thanks.
Yeah.
Okay, thank you. Anyone else has a question? Okay, I will read out Tomer's question. Can you speculate on what consequences implementing NLTE would have on your simulations? How large is the impact,
yeah,
basically?
Okay. Thank you, Tomer, for the question. Luckily, I'm on a very good slide to describe that. As you can see, when we are predicting the mass loss rate or dynamics of outflows, the NLTE and LTE models, so these red mass loss rates are coming from NLTE description, and blues that I'm computing here are coming from LTE description, agree extremely well, meaning that dynamics can be extremely well approximated with LTE assumption. Now, if you want to do exact spectrum computation, for instance, to create a synthetic spectrum, then you need to account for NLTE effects as line shapes and line strength will be dominated. If you are asking what will be dynamical effects, I think there will be very small influence. If you are asking what will be what will be produced spectrum, then we need to account for an LTE. But I think answer will be very little effect in such a scenario.
Okay, thank you. Anyone else wanted to make a remark or has a question? If not, then I would like to thank Luka again. Thank you very much, Luka. And then I will see every one of you next time. Thanks, you.